In this section, we're going to have a look at two circuit components that actually sense, or can be used to sense, the external environment. The first is a thermistor. So the symbol, circuit symbol for a thermistor, looks like a resistor to start with, and how it's different is it has this line going through it like that. And you would connect this into a circuit like any other kind of resistor, like this. Now, of course, using what we've developed in the previous video, the ability to determine the resistance of a component by fixing an ammeter and a voltmeter in the circuit, we can work out how much resistance is present in this thermistor. So we would have something like this. Now, sometimes people would ask me, how do you remember that that's a thermistor? Well, it looks like an ice hockey stick, and you play ice hockey when it's cold, and thermistor is sensitive to the temperature. It's not great. But come into the lab and let's do an experiment. What we want to find out is, how does the resistance of a thermistor change as the temperature changes? So this is the experiment that we're going to do to demonstrate how the resistance changes with temperature. First of all, we need something whose temperature is going to change, and that's going to be provided by this kettle. So I'm going to put some water in this kettle and plug this in. Now, what I've also got here is a data logger that can measure the temperature of things. So I'm going to put this into my kettle, like this, and it should measure the temperature of our water. Now, the water is roughly at room temperature, just slightly colder than the room. Now, with the thermistor itself, we're using a waterproof thermistor in a plastic sleeve. What I've done is I could connect this to a voltmeter and an ammeter to measure the voltage and the current, but what I'm going to do is I'm going to do a slightly quicker version of this. I'm going to use this multimeter on resistance mode. It's just simpler and more straightforward. I've got to make sure that I'm plugged into the resistor mode terminal and the common terminal down here. And to make sense of the scale at the top, what I found is that I'm in mega ohms, and my scale will go up to a maximum of 2 mega ohms. As I put this in the water alongside the temperature measurer, what I should find is it comes to a nice steady value. So here the temperature, here the resistance of the thermistor. Let's turn it on and see what happens. So our kettle is now on. And you can now see that the temperature is rising. As the temperature rises, you can also see that the resistance is falling. Now, this kind of thermistor is called a negative temperature coefficient thermistor because of the fact that as the temperature increases, the resistance decreases. You can see that it decreases rapidly to start with, but then more slowly later on. What would this look like if we were to plot it on a graph? Well, let's go and have a look. So what did it do? To start with, the resistance was high when the temperature was low. So we start up here, and it very rapidly decreased in resistance as the temperature began to rise. But then it started to then become much more shallow, and the resistance change became less and less for the increasing temperature. And there we have it. This is the shape of the graph of resistance against temperature for a thermistor. It turns out that thermistors are used in lots of technology, including thermostats, which are set to a certain value, so that if that temperature is exceeded, or it falls below that temperature, then the resistance in the circuit is such that enables a heater to turn on. Other such uses of thermistors include in electronics, to make sure that your computer doesn't overheat, to make sure that your phone's processes are within an amount that enables it to function without the temperature getting too high. The next component that we want to look at is the light dependent resistor, or LDR. Now, the circuit symbol for this one is, it looks like a resistor, as before, but quite often it's drawn with a circle around it and two arrows pointing at it, representing the light rays. Now again, we could use a voltmeter and an ammeter to measure the resistance across this component, or we could use the ohm meter setting of our multimeter. So let's go see the experimental setup that enables us to test this for ourselves. So here is the setup. What I've got is a source of light, this light bulb here. It's connected to a variac, which is just a ginormous dimmer switch. What I have just here is an LDR, and I've connected it to the ohm meter connection on my multimeter. Now, the resistance in this is different to the resistance in the thermistor, so I've had to change the scale. I'm now in kilo ohms rather than mega ohms. Here, I've got a data logger connected to a light meter. This is going to independently record how much light is present whilst we run this experiment. As it gets brighter, the light meter will give us a higher value, but what will happen to the resistance? Only time will tell. So quite obviously, we need to do this in the dark. So to start with now, we've got a light level of 4, and the resistance has actually got really high. So as we increase the light level, what we find is that the resistance now is 16, 15, 14, and it is getting smaller as the light level is getting larger. So we're now up to a light level approaching 20, and the resistance is down to 6 kilo ohms, and it is falling still. So here we can see that the resistance is continuing to fall as the light level continues to increase. Now, very similar to the thermistor, the resistance decreased quite rapidly to start with, and then more slowly afterwards. Now, we've nearly hit 1,000 on our light meter scale, and I think this is the best place to stop. You could do this experiment, rather than varying the light level through the light bulb, you could do it by changing the distance between the LDR and the light bulb, knowing that how bright this appears at the LDR is going to decrease with distance. If we were to plot that data on a graph, you can see that what happened was that the resistance fell as the light intensity increased. It was really rapid to start with, and then it became more and more and more small of a change with increasing light level. So the graph looks very similar to the graph of a thermistor. You've just got to remember that we're going from low light to high light, and you're going from low temperature to high temperature in the two graphs. Now, LDRs like this are used in all kinds of technology, including in things like street lights. When the light level drops to a certain value, then what happens is the resistance goes right up. And that triggers another circuit to turn on the light. Now, here is one last thing to consider. The usage of an LDR and a thermistor might change depending on the desired outcome. For example, if you wanted a fan to turn on because it was too hot, that is a response to warmth. That is a response to a high temperature. But if you want a lamp to turn on when it is dark, that is actually a response to a low light level. And so whether or not your responsive circuit needs to respond to a high and therefore low resistance through your device, or a low, which would be a high resistance through your device, it depends on the circumstance. But we don't need to go any further into that because we're now going into the realms of electronics.